It's my great pleasure to introduce tonight's speaker, Lakshmi Narayanan Mahadevan. But I should tell you that he's the Lola England Developing Professor of Applied Mathematics, Organismic and Evolutionary Biology, and Physics at Harvard University. So while he was trained in applied math, getting his PhD from Stanford in 1995, you can see from that long list of departmental affiliations, he has a very broad intellectual interest in his research. So maybe simply put, his research is looking for mathematical principles to understand the organization of the matter all around us. And so for this research, he's received too many prestigious awards for me to list. I'll simply note he received in 2009 a MacArthur Fellowship, and recently in 2016 he was elected as a Fellow of the Royal Society. So that's all the embarrassment I'll do for tonight. So tonight Maha's talk will describe the intersection between art, science, mathematics, maybe a little bit of engineering, we'll see, through the study of origami. And with that, please help me to welcome him.
Thank you very much, Greg. Thank you all for coming. So what I wanted to do over the next 55 minutes or so is to tell you about some aspects of origami, which of course is a very ancient subject in art and a much younger subject in science. And this seems to be rather typical of many of these kinds of disciplines, which start out in the world of playing with things, crafts and related issues, and then gradually in science we begin to realize how powerful these ideas could be if we understood how we are essentially able to deal with them. So if one wanted to start with art, a question might be to essentially ask how you might create or tame this dragon. This is made of a single sheet of paper by this fantastic origami artist Kamiya. One might ask about how you can use what we know about artificial origami, or turn it around and ask, are there natural examples of origami, and understand how these natural patterns associated with folding, which is very, very typical of origami, arise. This is a piece of paper which is folded. This is a leaf which is in the process. Some leaves are in the process of unfolding. This is a piece of Jello that's dried for too long. And this is a calculation. And then eventually, if we can understand them, could we eventually make some sense and even engineer shape? So you want to go from these ancient arts to thinking about physics, mathematics, science, and then eventually moving towards engineering. Although I don't think, if I implied, I don't mean in any way that this is a linear way in which we think about these. We continuously go back and forth. So if I think about origami from the point of view of art, it seems to have originated pretty much with the invention of paper. Paper, we think, originated in China more than 2,000 years ago, and very soon after that, people started to play with it. Okay, you flatten out different kinds of fibers, and once you flatten them out, then it becomes relatively easy to manipulate them, and the ancient art of paper folding in Chinese is called zhe. Of course, what's much more commonly known in the West is the Japanese view of the subject. Paper came from China to Korea and to Japan a few hundred years later, and started to have a very important ceremonial purpose. Typically in Japanese custom, people folded various kinds of butterflies and gave them as presents or burnt them as offerings to various deities. And in fact, the word itself, as I mentioned in the abstract, origami, comes from the Japanese for oru, fold, and kami, paper. So these folded objects were initially playthings, then became objects or ways in which we or people started venerating their ancestors. But if I ask you here, what is the first thing that comes to mind if I mention origami? Perhaps it would be, especially if there are young people over here. I don't see many young kids. There are. Okay. What do you think of? First think of origami. Maybe a crane? Okay, I told you, all right? Okay, so in fact, at least that's the way I came to know about origami when I was a lot younger than I am now. This is essentially the pattern of folds on a square sheet of paper, the red and the blue corresponding to whether I have a mountain or a valley. I'll come back to that. And if you fold it without getting too frustrated with yourself or with a sheet of paper, you end up with this structure. In The 1940s and slightly later than that, it became very famous. The cranes became very famous thanks to a very poignant story associated with a young Japanese girl who was 2 years old when the first atomic bomb was set off in Hiroshima, Sadako, and in fact, she tried to build 1,000 cranes, and she died 12 years later in 1957. And was able to only make 600 or so of those. So this is essentially what we think of when we think of origami archetypically, a piece of paper folded into a crane. But you can essentially ask about other ways in other kinds of art forms associated with origami, and I don't know why the top has come off. Typically, we think of origami associated with using sheets of paper and then folding them just by drying. I showed you the dragon. And this dragon, and the one that I showed you on the previous transparency, is made by making straight folds. Over the last 50 or 75 years, there have been various attempts to essentially move beyond straight folds and use curved folds. And a spectacular example of this, which you can actually see in the Museum of Modern Art in New York, due to the father and son, Eric and I can't remember the father's name, the domains, you have these fantastic curved folds. So where you're taking a sheet of paper, in this case, creasing it partially along curves and folding it. And you get very, very beautiful forms. So both straight folds are possible and curved folds are possible associated with dry origami. But pieces of paper are made of wood. And as you know, if I take a paper back and left it in the kitchen for too long, or I left it in the bathroom for too long, it starts to curl up, and it curls up because it swells, and it swells differently on one side compared to the other. And so over the last few years, people have started to ask, can you essentially do the same thing, but now use printing? So imagine instead of printing ink, of course, ink has both a dye and water, typically. Imagine that I was just printing water onto a piece of paper in an appropriate pattern. Then you can start asking about questions which are related to wet origami. So here is an example from an architect from a few years ago, where he takes a flat piece of paper, pushes it through a printer, and paints along a particular pattern. And because the paint, or in this case the ink, is put on one side, it swells on that one side. A consequence of that swelling is that the sheet deforms. As it starts to deform, the whole thing self-folds out of the plane. And of course, where this comes from is the inspiration from nature, and something that I think all of you should try. Again, I see a few children over here. I hope they will at least encourage the adults to do so, which is to take your pine cones, which are now drying, and put them in water. How many of you knew that if you take pine cones and put them in water, they will essentially close? Oh, see, the only people that matter did know. Try it. Okay, you put it in water, it will close. You take it out, it will essentially open again. And this is a remarkable way in which we think these pine cones have the ability to essentially disperse their seeds at just the right time, so that as it starts to dry, the pine cone opens. As it opens, the seeds are dispersed. But when it's wet, it doesn't make much sense, typically because it's either cold or not yet the right time of the year. So if I'm thinking about now origami from the point of view of asking whether I can do something with dry paper or with wet paper, can I essentially ask whether I can build structures on the scale of what I can control with my hands? I can then ask, can we essentially broaden that perspective and move much beyond? As always, art inspires many other disciplines, and the architects were very quick onto this. In the 1920s, in fact, the Bauhaus architect Walter Gropius had a student called Joseph Albers, and Albers in his studio essentially started having students basically play with pieces of paper which they folded into a whole bunch of patterns which they wanted to try and use as models for architecture. And I think much later, in fact, Louis Sullivan said that the reason for all this to happen is that in architecture, form ever follows function. So over here, playing with the idea, asking questions about how you might enclose structures cleverly using a single sheet of some object. In this case, it was paper. That was pretty much the obvious thing to start with. Can you essentially do clever things? So the Bauhaus architect started that. A little later, Ron Resch, another architect, did the same thing on a slightly larger scale. So these are essentially on the scale of my hand. You can see people over here. Ron Resch essentially built this little tower out of paper on a scale of a few meters and started this movement of asking how you may follow Sullivan's dictum and use thin sheets or pieces of wood or metal, and now increasingly glass, to follow function. How do you essentially create form to follow function? Of course, that also raises the question in reverse. I've shown you examples of artificial origami. Are there examples of natural origami? And the answer is yes. In fact, in biology, we can turn Sullivan's dictum around and say that equally, not only does form follow function, but function equally follows form. My lungs are very tightly folded objects. My intestines have lots of folds. My brains have folds. All these have functional consequences. I have the ability, maybe I don't, but I hope all of you do, to process some information precisely because I have this folded cortex on top of my gray matter. In my lungs, I have the ability to essentially take up air much more easily, even though in a small volume I have a large amount of area. Similarly, in my guts. Do you see origami, in fact, in biology as well? And you do. Here is an example from the hornbeam leaf. You see this in the hornbeam. You see this in the beech. I don't know whether you have hornbeams in beeches over here in Aspen. I see people nodding. So next spring, please make sure that you take a look. These are different stages of the leaf unfolding, and you see these characteristic linear, straight folds, and as the leaf deploys, the whole thing essentially unfolds. You also see this in a completely different setting in insect wings. Okay, so this is an unfolded insect wing, and what is being shown over here is that the four folds associated with it, which allow the wing to essentially be folded and be hidden inside something called the elytra, the shield. If you watch ladybirds, you often see these beautiful elytra, but in fact, when it flies, what it does, it first unravels the wings, opens the elytra, the wings unfold, and then it flies away. And I'm going to show you that in a video due to a recent Japanese investigator, Saito, showing the rove beetle, where you can see that the wings unfold from below the elytra and it takes off. Okay? So origami appears in art, origami appears in science, origami appears in architecture, clearly, inspired by art. And there's a very natural question associated with it, which is how, and there is a natural solution that, in fact, the biology tells us has essentially appeared a long, long time before engineers ever thought of it. 50 million years ago or before, these objects, leaves and insect wings, are naturally deployable structures which are packed when they need to be packed and unpacked when they need to be unpacked. Of course, in this case, it's never reversed. In the case of the insect wing, it's also capable of being reversed. I don't have a video of this. So the natural question that this raises is, how do these patterns arise? Another natural question that this raises is, can you essentially control these patterns? A third natural question that arises is, can you essentially design the folds like what I showed you before for the crane in order for you to end up with a particular pattern at the end of the day? So all these are obvious questions. Artists have had a running start on this. Scientists are gradually starting to catch up with it. And I want to try and address some of these things. Okay, so I see that there's been an out of order over here. So I'll first tell you the reason why these patterns arise naturally in many of these physical or biological systems. And a very simple way to think about it is the following. Imagine that I had a thin sheet like this piece of paper, but it was not free. It was attached to some substrate. It was attached, for example, to this table or something much softer. And that soft object started to shrink in both directions because of drying, or this thin sheet started to grow relative to the substrate. A consequence of that is that the substrate, the Jello below, for example, or the wood was not essentially growing as much as the surface, so the surface is put into compression in both directions. And if it's put into compression in both directions, it can start to essentially form wrinkling instabilities. And we see this, in fact. This is an example of drying gelatin where spontaneously you see these zigzag patterns arise. You see the same thing, in fact, in your gut. Not now. This happened when you were in your mother's womb, when you were about 20 weeks old or so. The same zigzag patterns arise during the process of gut formation, and one can make some theoretical estimates of how this arises, and I'm just going to show you a consequence of a little calculation that I was fortunate to be involved in over here, where you see essentially the gut growing, the outer layer is growing, the inner layer is also growing, but the inner layer grows much more. If the inner layer grows much more, what seems to happen is that the inner layer is squeezed. A consequence of the squeezing of the inner layer is it starts to wrinkle, and as it starts to wrinkle, you start seeing these patterns which eventually end up like this. So in a very simple-minded way, we can understand how these origami-like patterns arise in nature simply because of the relative growth of different tissues compared to each other. In the leaf, one part of the leaf grows compared to the other. In the gut, the same thing happens. And we can even start making sense of this from a physical, mathematical perspective. So I've told you about art, I've told you about architecture, I've told you a little bit about how these natural patterns associated with origami appear in biology. I now want to switch to what we can do with them, or what people are starting to think about them. Okay? So architects, of course, have been playing with this for a very long time, but even before that, people in textiles have been playing with this. So this is a painting from the 16th century by the artist Bronzino. And you may be, at least if you're in the first couple of rows, be able to see that the woman's brocade in this dress, in fact, has a zigzag pattern, very similar to a modern version of a scarf, which I will never be able to afford. Okay? A much more recent incarnation of the same thing is an origami pattern on a person's hand due to the architect Neri Oxman from MIT. So on the medium to large scale, architects have essentially explored origami, textile engineers, tailors, couturiers have essentially started to explore origami, and there is a third view of how technology has essentially used origami, and that is, in fact, the inspiration for much of what I'm going to tell you about, and much of what a lot of people over here over the last week and the next couple of weeks have been inspired by, which is a Miura-ori fold. Ori, remind you, is a fold. Miura is a Japanese engineer, an astrophysicist who essentially came up with this, not realizing that biology had essentially beaten him to it by 50 million years. And what he did was to solve the problem of how to fold a map and how to unfold a map in a sensible way. Okay? So this is the map that I was given. It was folded and given to me like more or less like this. I folded it a couple more times so it fits in my pocket. And if I wanted to open it, what I do is I open one fold, and then I open another fold, and then I open the third fold, and I open a fourth fold. And each one of these folds is independent of the other. Okay? That's easy enough to do. Now, if you're in a car, or at least if you were in a car in the 20th century, and you had to essentially struggle with opening a map when you were trying to find your way, not too much of a problem. But you were trying to close it, there's a problem. And there's a problem because once it's flat, I'm not quite sure which fold to start with. And maybe, I don't know. Okay, there's already a problem. Okay, maybe this way. That doesn't work either. Okay, so I think it's this one first. Actually, that's not true either. So what's the issue? The issue is that when I have these independent folds which are orthogonal to each other, which are at 90 degrees to each other, I have two possibilities for every unfolding, or in this case, folding. All right? So as I'm trying to fold, I have two possibilities for every fold, and therefore if I have n such folds, I have 2 to the n possibilities, which very, very quickly becomes very large, and so that's a problem. And this is a tribute to human stupidity. Okay? Because the only way in which you can fold a map so that all the folds are independent of each other is when the folds were at 90 degrees to each other. Any other way that you did it, all the folds will essentially couple to each other. The simple example that I showed you of the insect wing is exactly that. This is the insect wing, abstracted, okay? And if I essentially open it out, the whole thing unfolds. The whole thing folds in one motion. That same idea, now on a larger scale, this is the map that I was given here to find my way home, which I folded an hour or two ago. The whole thing unfolds in one motion, and the whole thing folds in one motion. Okay? And Miura essentially recognized that and patented it. And since then, a lot of people have used these ideas in various different settings. For example, there are tents which essentially use this idea. There are solar sails which use this idea. And on a small scale, that same idea of combining the motions in a way which allows you to either unfold or fold in one continuous motion, people have now started to use on the small scale, not just on the medium to large scale. Here is a set of images from a structure which is capable of folding itself. So you basically have a sheet on which you have some wires, and these wires essentially conduct electricity, and they can be heated, and so as a consequence of heating, they expand, and so they essentially push this into different shapes. You can have deployable stents, so the whole thing can be collapsed and stuck into an artery if it's needed, and then due to the temperature variations, the whole thing will open. You can go and actually create self-folding or self-unfolding robots, and if you went down even smaller, people have started to ask whether you can essentially take materials, in this case a single layer of carbon, which is one atom thick, called graphene, and build in folds and ask whether you can essentially create nanomachines. So these are ideas that people essentially have. And what you've seen, what I hope you've seen right through, is in fact that in all these problems, independent of scale, independent of whether I was thinking about architecture or art or engineering or in science, every single time the question boiled down to one. Can we essentially predict? Can we design? And can we control shape? That's the fundamental question. We understand what it means to predict, we understand what it means to design, we understand what it means to control. What is shape? Okay. Seems obvious. Okay. In fact, I don't think it is. The statistician David Kendall defined it in terms of negatives. He said shape is what is left over after I've removed translation, rotation, and scale. So you can recognize me independent pretty much of how far I am. As long as I don't go too far away. You can recognize me if you turn your head, and you can recognize me if you move far away from me and move to one side or the other. So translation, rotation, and scale. That's what he defined it as. What's left over after that is essentially shape. And geometrically, that is indeed correct. But from the point of view of perception, from the point of view of recognizing me, I can't go too far away because I just lose resolution. From the point of view of function, for example, if I'm thinking about the lung or the brain or the gut, in fact, shape is scale and can be scale dependent because different things potentially are associated with what happen at different scales, and as a consequence, you can have folds within folds within folds, which you will blur out and which don't matter for absorption in some situations and which do matter in other situations. And from the point of view of physics, clearly scale is important. The range at which I'm looking and trying to understand things matters. So even though technically from a mathematical point of view the statement is correct, from every other point of view it's not complete. Okay? So if we want to understand how to design, predict, and control shape, we have to first understand exactly how this happens on different scales. And if we want to do this, and we've given up the idea of basically being exact, then we are starting to think about approximation. And this is what origami is all about. This is what architecture is all about. This is what many of the technological applications that I told you are all about. How can I take a flat sheet of paper and from this flat sheet of paper approximate something which is arbitrarily complex and curved? Okay? So here is a sheet of paper that I crumpled, and now I've opened it up, and it can do remarkable things. Okay? For example, I can take this sheet of paper and I can drape my arm. I can approximately drape my elbow. I can even make a hat, and if you were bold enough, you could even sell this for a lot of money. Okay? How do you essentially think about approximating curvature from folded sheets, which are nominally flat but have these sharp creases, is a natural question that arises as soon as we start asking about scale-dependent objects. And then there's a next natural question, which was again asked by artisans and artists a long time ago, which is how do we transform shape from one kind to another? How do I essentially build shape-shifting objects? How do I essentially deploy them, like that insect wing, like the leaf? So what I want to do now over the next 20 minutes or so is to essentially walk you through a little bit of mathematics and a little bit of physics to essentially say how we and a lot of others are trying to essentially look at these kinds of questions. Okay. First thing is everything that I've told you about is associated with playing with two-dimensional or approximately two-dimensional objects sitting in three-dimensional. So in three dimensions. So I have two-dimensional objects. Actually, it's 2 plus a small amount of thickness. And these are pervasive in everything that I've told you about. They're not pervasive everywhere, of course, but these are pervasive in all the examples that I've picked up. There's an immediate consequence of the fact that these are very thin objects, and that's associated with the fact that as soon as they are very thin, you have experience, and this can be made mathematical relatively simply, that these thin objects are very, very hard to stretch. They're very, very hard to essentially deform in the plane. I can't make different parts move relative to each other, but they are very easy to bend. Okay? And this property is essentially not dependent on the material. It's true of paper, it's true of metal, and now we increasingly see it being used as being true of glass. Okay? Flexible electronics that people are talking about is based on that simple idea that if I make the glass thin enough and relatively free of defects, I can essentially fold up that piece of glass and put it in my pocket and walk away. So it's not so dependent on the material. There is a weak dependence, but for most practical purposes, that's not important. Furthermore, I've already shown you, and you know how to experience this yourself, it's very easy to bend, and the whole point of origami, the whole point of many of these structures that I told you, is that it's so easy to bend that it's very easy to make these sharp creases, and these sharp creases have memory. So that means I can essentially build material which has memory, even though all the memory, or maybe because all the memory is now accommodated in geometry. And if I think about origami, there is a tradition of calling folds by two names, mountain folds and valley folds, and you can then color up your flat sheet with mountain folds and valley folds, and then if you know the order in which you essentially fold these individual edges, you end up with a crane or in tiers. Okay? Complex origami, not just these simple mountain folds. It's worth again pointing out that everybody uses and bandies about this word complexity all over the place. The origin of complexity, in fact, comes from the Latin com is together and plicare to fold. So complexity fundamentally is associated with a very simple thing that we do all the time, fold pieces of paper. It's important to do it sequentially. I told you why, you know from experience, and therefore the order matters enormously. Okay? I've already given you. So this is our old crane, which essentially has a pattern over here, blue corresponding to the mountain folds and red corresponding to the valley folds. And if you order your folds appropriately, then you end up with a crane. I also showed you that you don't have just straight folds, you can have curved folds. The most beautiful and familiar example of a curved fold is your collar. Okay, if you have a stiff collar, and I have a stiff collar today, in fact, it's essentially a cylinder. And what you do is you build a crease on that cylinder, which is slightly it's not essentially parallel to the axis or the longitude, and then you fold it, and when you fold it along that, you get this beautiful structure. Another obvious place where you get curved folds is if you've ever gone and bought a box of fries. It also starts out as being flat packed, but you look at it carefully and it has curved folds, and those curved folds, when you essentially build the box, you've got to fold the object along these curved folds. So mathematically, these objects, these flat sheets, even though they are built into cranes or collars or fries boxes, are piecewise essentially just parts of the plane. Okay? They're just different copies of the plane which are pasted together, and they're pasted together so that there are no gaps anywhere. Now, that's a very easy thing to state. It's an extremely hard thing to make mathematical because it's saying that I cannot essentially move any elements in that sheet of paper to change lengths or to change angles. That means also that it's very easy to build cylinders, it's very easy to build cones, and a small generalization thereof, but that's it. Beyond that, you've got to struggle, and the way you essentially get around that is by building creases and then folding along these creases. So this is the nugget and essentially the most difficult part of how we have to get around or how we have to handle the problem. How do we build this ugly constraint into the problem? There's a little more mathematics that I'd like to introduce to you, also using a simple set of examples. And the first example that I want to use is essentially the same map that I essentially showed you a couple of minutes ago. It has two flat states. I will dare not open this up completely, because if I do open it up completely, it suffers from the same degeneracy as these orthogonally fold maps have. But if I open it up almost completely, you see that it is capable of being flat in one state and equally capable of being flat in another state. And this is very common in origami, and it's in fact one of the powers of origami, because you can essentially fold it, put it in your pocket, and walk away. And eventually, if you wanted to have a lean-to or a tent or something of that sort, you can do exactly the same thing. You can pack it, and then you can unpack it. And that essentially is this notion of flat foldability, or flat origami, or flat foldability. And I want to, again, very quickly, without getting to the details, tell you about what that means with this little example over here. So this is the building block of origami, this insect wing. It has one vertex, and it has 4 edges which come together, 3 mountains and 1 valley, or the other way around, doesn't really matter. And obviously, if I go around this vertex once, I've gone around a circle. So I have 360 degrees worth of angle. And so if I look at the angle that each edge makes with the other in the plane, they must all add up to 360 degrees, 2 pi, one circle. That's essentially saying what I told you before. I'm not tearing it, and I'm not pushing 2 things so that they overlap physically in the plane, even though they can overlap by coming out of the plane. But there is a second, much more subtle idea, and the subtle idea and the second idea is that what I'm doing when I fold it into something which is flat is that I'm going back and forth. Okay? Because I have a fold. I start with that, I fold this way, then I go backwards, then I come back forwards, and I go backwards. And I have to essentially do that when I go around. And that leads to a second condition, which all I'm going to tell you boils down to saying that all the angles, in addition to adding up to 2 pi, also means that opposite angles add up to half that, to 2 right angles, effectively. And this is a very powerful, very simple idea, but it's got very immense consequences. Okay? And so this raises a third question, and I should have remembered, I forgot to bring a paper bag. All right, okay. So I'm going to ask you to imagine. So all of you have gone to grocery stores, and now there is a tendency for everybody to use paper bags instead of plastic bags. And you know that your paper bag folds up, and then you can pack it and stack it, and then you come to the grocery store, you open it up, and then you can fill it. Question, how many of you think, I think I've already given you the answer, how many of you think you can open up a paper bag without ever stretching any part of it? Yes?
Yeah, I think you can.
And that's what everybody does. And in fact, until 3 or 4 years ago, that's what the community thought, and the answer is no. Okay? From a mathematical point of view, which means what? By basically asking, do I satisfy these conditions on the angles? Do I satisfy, and if I satisfy the condition that I cannot change line lengths and angles between lines, can you do this? The answer is no. Okay? And this was proved. I'm really sorry that the bottoms and the tops of these slides are falling off. This was proved by a Chinese mathematician and engineer at Oxford, and he essentially showed that this was possible or impossible by building a paper bag with sheets of metal. Okay? And showing that there is a tendency to rip, or equivalently, you've got to push hard enough to essentially cross a barrier. Okay. What does this mean? It means that what I've told you about so far, all the mathematics is not sufficient. I have to worry about the fact that this is made of a real object, and real objects essentially stretch, and real objects essentially, it costs you energy to deform them, to stretch them and bend them and so on and so forth. So if I think about it now from a physical point of view, I can ask, where do I start? Because the complexity, quite literally, of origami is so vast, where do we even begin to understand and ask these questions about, is it possible to fold, flat fold? Is it possible to create anything from a flat sheet of paper? From a crumpled sheet of paper, it's possible to do almost anything. But can I essentially have a tension between complete disorder that you see in a crumpled sheet of paper and perfect order? And so how do we start? We start by looking at the case of perfect order and then gradually building in, maybe not disorder, but modulations of order. So I want to start with this very simple problem, again, the problem that I introduced before, which is associated with this object, the Miura-ori map fold, shown over here. It has peculiar properties. I already told you that it has one peculiar property associated with the fact that the whole thing opens when one motion. It has another peculiar property compared to other materials that you may be familiar with. Most materials you're familiar with, if I pull in one direction, will contract in other directions. I take a rubber band and I pull it in one direction, and it will start becoming thinner and thinner in the other directions. But this object, even though the actual sheet of paper itself behaves the same way, if I'd flattened it out and stretched it, the folded piece of paper has unusual properties. If I pull in one direction, it also expands in the other direction. Okay? Moreover, and this is not big enough for me to demonstrate it, if I try to bend a sheet of paper, it will just bend into a cylinder. This object will just bend into a cylinder. But if I take this object, and I think of this as an effective material, if I try to bend it in one direction, you see what happens along the edges. Okay? So it's got curvature in one direction induced by me, and in the orthogonal direction, the perpendicular direction, it starts to behave and curve in the opposite direction. So it in fact behaves like a saddle. And so it does things which we are not typically familiar with. I can create curvatures, exactly what we were planning to do, what we were hoping to do, due to this. Okay? So this is in fact an archetype of a mechanical metamaterial, a material which has unusual properties which you would not expect based on its constituents, but in this case, based on the geometry, it does these bizarre things. Not so bizarre when you think about it, but initially at least it sounds and seems like it's bizarre. It expands in both directions when it pulled, it can bend into a saddle, and what I told you about before, that it's globally coordinated. I can essentially open and close the whole thing in one motion, unlike the usual maps. Can we now unpack the complexity of this? I told you that we want to start with a very simple, perfectly ordered case, and if I look at this and I stare at it, in fact, what it is just a number of copies of the unit cell shown over here, each one of them corresponding to this fold pattern that I showed you, this minimal fold, and you just make many copies of them and you glue them. You glue them in one direction, you glue them in the other direction. So a single mountain valley fold, and you glue them in both directions, and that's it. So in order to understand that, we just have to repeat this pattern. I told you it's essentially capable of being flattened onto a sheet of paper without bending or stretching. I also told you that in fact it is what is called rigid foldable, but now I'm defining that. Rigid foldability simply means that I can go from the flat sheet to another flat configuration continuously without ever violating changes in length or changes in angle, unlike the paper bag. And then finally, I told you, and I'm showing you now again, that it's flat foldable. Okay, so this is essentially characterizing this minimal structure, and then based on these mathematical ideas, one can start asking what the physical consequences are. How easy is it to stretch it? How hard is it to stretch it? How easy it is to bend it, and how hard it is to bend it, and so on and so forth. And we and a lot of others over the last few years have started to essentially make sense of that from a physical point of view, doing experiments, doing theory, and so on and so forth. Additionally, the community has also started to address the question of what you would do when the folds are not straight folds, but the folds are curved. The example that I showed you from the Museum of Modern Art abstracted into this very simple picture over here. And how is this made? And again, this is an invitation for at least the younger people to try it out. You basically take an annulus, you cut out an annulus from a piece of paper, and then you pre-crease along the center and try to fold it. Okay? And what happens is that when you try to fold it along the center, the outside and the inside have lengths which are different, and in order to accommodate the fact that when I bend it, they are moving along different circles, what actually happens is that it forms this saddle. And you can, again, make sense of it mathematically. You can build physical models, and you can start doing computations as well to understand its properties. What do I mean by properties? You can understand what the shape is, you can understand what the response is, and then start asking how you could control this by playing with the width, the length, and so on and so forth. More recently, others have shown that, just like you would imagine, because the folds have memory, a single fold effectively already has memory. What happens if I have a collection of folds? And I'm showing you just a set of images over here from a very interesting paper published a couple of years ago, which show that more or less the same folding pattern that I showed you. The Miura-ori has some hidden degrees of freedom which allow you to swallow some of the paper. So you can essentially fold it so that some piece of paper which was visible to you starts to hide. And a consequence of that hiding effectively is associated with the fact that I can now approximate curved objects, objects which are curved in 2 dimensions rather than just 1 dimension. Okay, I want to finish then by telling you a little bit about what one might do from the point of view of design and control. So I've walked you through a little bit of the history. I've told you a little bit about approaches which introduced some mathematics and physics, and now I want to turn the question around and ask, can I not just predict how these patterns arise and how they behave, but can I essentially design the fold patterns on a plane which will allow me to fold the sheet into any shape out of the plane? Okay? An engineering question, but also a very, very difficult mathematics question. How can we program curvature? So how can I essentially take a midline or a middle path, if you want, between the perfectly ordered Miura-ori, the map that I showed you, the almost perfectly disordered, in fact, you cannot ever get perfect disorder, but something which looks messy. How can you go between them? How can you gradually, rather than abruptly go from one to the other, how can you gradually move from a flat sheet and a perfectly periodic set of folds to something where you can, in fact, for example, can you build a torus? Can you essentially build a donut from a flat sheet of paper? A very old question posed by a mathematician in the 19th century, Gauss actually, and Riemann, and in one sense settled by John Nash, a mathematician I'm sure you've all heard of in the context of economics, but he also had some very profound and far-reaching results in differential geometry, and one of them was to show that if you give up certain conditions associated with smoothness, you can in fact take a flat sheet of paper and create a torus. But he didn't give a construction for it. He simply said that you can do it. And our question, and we don't have a complete answer to this, is can we essentially somehow go between these two extremes and create any shape that we want? Okay, so that's the question. Can we inverse design, fold patterns on a sheet of paper, tell you, or you tell me how to crease, so that when I fold along these mountains and valleys, I get all the properties that this simple object has, that it must be capable of being done with a single sheet of paper, which is not creased, which is not torn anywhere, excuse me. It may be possible to essentially flat fold it, so it has a second state, which I can put in my pocket. It may be possible or not to essentially do so in one continuous motion, and if it's done in one continuous motion with just 1 degree of freedom, that would be fantastic, because I don't have to struggle. Okay? So that's the verbal version of the question. In a pictorial way, this is essentially our perfectly periodic lattice, which we started out with. This is the periodic cell. Here I have 4 such copies. How did we do this? How did we solve the problem? We give up something, because if I want to take this crumpled sheet of paper, or if I want to take this Miura-ori and drape it around my head, what I'm going to do is I'm going to allow some vertices to attach to my head so that they approximate my head, and others to be free. But I give them only the certain amount of freedom that I need minimally in order for me to be still able to satisfy at least approximately some of these conditions. Okay? So pictorially, we give up or we free some of these vertices. The red ones, we allow them to be free. The blue ones, we attach to whatever surface I want to essentially try and drape the sheet of paper onto. And then we move the red ones so that we can approximately satisfy these conditions. So for example, going from the simple mountain valley fold associated with the unit cell, we move the vertices around and we can still fold it, but now they're essentially not going to be periodic anymore. So I've given up perfect periodicity. Okay? What are the constraints? I won't belabor them too much, except to point out that they are what I told you before, that in fact at every vertex, because I'm not tearing it, the angles must add up to what I would have when I go around a circle, 2 pi. These sheets are made of flat facets, so therefore they have 0 volume in the limit of 0 thickness. So that's a second constraint. And then there is this third constraint, which I tried to illustrate, where I have to go back and forth, which means that the sum of the angles opposite to each other must add up to pi. And that can be cast as a mathematical optimization problem, which is to determine those free vertices that I showed you in the previous transparency or slide to best approximate the given shape with these constraints. Okay? So you've got to solve the mathematics problem. From a computational point of view, from an engineering point of view, the question that we are asking is, can we become a tailor? Okay? The job of a tailor is a tremendously complicated one because he or she essentially takes a flat sheet, cuts it, stitches it, and it fits you. It's a very difficult mathematics question. Even without stitching, without cutting and stitching, it's difficult. With cutting and stitching, it becomes impossibly hard. So in this case, we're only allowed to fold, and I'll show you what we can do. Okay? So we can essentially construct computationally the ability to take a flat sheet of paper and in the plane allow it to drape any curve you give me. Okay? That's a theorem. In fact, that's a real result, not an approximation. We can approximately, I will not get into the details, there are some technical details. We can also drape a sphere. So this object is not curved at all in the direction perpendicular to the board. It is curved in the direction of the board. This object is curved in both directions, but in fact, it's got the same kind of curvature, same sign of curvature in both directions. So it's part of a sphere. This object is like a potato chip or like a saddle. Also, both these are made of a flat sheet of paper. This is in silico. When I say made, it's computed. And then we can mix them. So here, for example, in this pill, we have a region in the center, which is like a cylinder, and a region near the tips, which is like a sphere. In this candle stand, we have a region in the center, which is like a cylinder, and near the ends, it's like a saddle. And in this flower vase, we essentially have the bottom close to a sphere and the top close to a saddle. So what am I telling you? I'm telling you that not only can we construct surfaces of zero curvature, positive curvature, and negative curvature, but piecewise combinations of them. And that's what a tailor tries to do, right? Because he or she essentially is trying to gradually stitch together from a flat sheet the ability to drape a complex object like the human body. And even more beautifully, the body itself does that. The body starts out as a single cell, divides a number of times, and somehow starts to essentially self-organize. So that's another metaphor. Okay? So all well and good on a computer. Can you essentially do this in the world? Levi Dute, a graduate student working in my lab, spent a month basically playing with thin sheets of paper and created these objects. Okay? These are not computations. These are real objects. I cannot bring them on a plane because they are about that size, at least the biggest ones. Okay, so that suggests that it's possible. It doesn't tell you that it's easy. And that's a question which we don't know how to essentially resolve at all.
How many flat sheets?
Thank you. Yeah, so this is a single sheet. This is essentially 4 or 6 of them because it's actually symmetric. This is a single sheet, and the same for these as well. So
the bottoms are all single?
No, they're not. Sorry, because we deliberately chose axis-symmetric objects so that we can essentially get one part and then rotationally. Yeah, thank you. Yeah, it's too difficult otherwise. Okay, so I am pretty much almost done. Can we essentially build shape-shifting objects? The answer is yes. So here is an animation of exactly what I showed you. Let me play that again. Okay, started out as a flat sheet of paper. It folds in one direction and folds in the other direction and eventually collapses. So this is, may have implications for architecture. Can you have memories? And the answer is again yes. So this is a saddle. And the way this calculation was done is by pinching one of these unit cells somewhere in the center, and the whole thing folds up because, as I said, it has a single degree of freedom, but you cannot do it without costing energy. So you have to essentially increase energy before you decrease it, which means it can essentially store at least these two states as low energy modes, and so it may have implications for machines. Okay. You can also ask questions about how much you're willing to pay to get an accurate representation of your surface and how much effort you want to essentially put in. So these are approximations of a hyperbolic surface of revolution. Here I have a few folds per unit area, so I'm doing a relatively poor job of approximating the smooth surface. Here I've increased the number of folds and facets by 10-fold, and here by another 10-fold, and I can do better and better. Of course, it costs you. Okay? If you are willing to essentially spend hours and days and months, you can get something smooth. So you get something which is very accurate, but the effort is very high. And the effort in this case is measured in terms of the number of folds. And so what is plotted over here is the cost as a function of the number of folds. And this minimum in the curve corresponds to the optimum where you're balancing accuracy and effort. All right, so I'm pretty much done. I want to tell you what I tried to say so over the last 50 minutes or so. So as in many of these systems associated with the everyday world, typically things start out in art, in this case in textiles, and over centuries moved into architecture, and that's true for origami as well. From a mathematics point of view, I at least alluded to this very, very beautiful set of interesting and tantalizing connections. We don't quite know what to make of them yet, and they're fundamentally associated with how do I embed one kind of object in another kind of space, one object of one dimension in a space of another dimension. In this case, a two-dimensional object, two-dimensional sheet in 3 dimensions. Can I do this smoothly? If not, what are the prices that I have to pay? What are the costs associated with that? And so there are some very beautiful connections to these ideas from going back all the way to Riemann and more recently to Nash and Gromov. And we've started to essentially address some tiny bits of it using ideas from optimization. I told you that origami appears very naturally in many systems, for example, in the gut, in leaves, and so on. It has implications for machines, and there are many, many opportunities, all of them which somehow are at the border and the boundary between perfect order, in which case it's kind of boring, and perfect chaos, in which case it's essentially almost intractable and equally boring. Okay, so none of this would have happened except for the fact that I've had the opportunity over many years to work with some wonderful people. Jian Wei and Levi were graduate students in my group who've moved on. Etienne Vuga was a postdoc, and we've also had collaborations with many of the people who are here or who were here at the Aspen Center. Chris Santangelo, his student, Marcelo Diaz, and a couple of colleagues from Harvard are going to be here soon, and Tomohiro Tachi, a wonderful origamist. I will finish by telling you about what one would like to do. Okay? How can we essentially really become tailors? We want to now add to the complexity of folding the complexity associated with cutting, which means I'm essentially now changing the connectivity itself. And I'll just stop with this beautiful example. This, you may recognize, of course, is the World Cup in soccer. This is the new soccer ball, which was debuted, I think, for this particular World Cup in Brazil. And it may or may not surprise you that this is not a sphere. Well, it is a sphere, but mathematically it's actually a cube. It's a 6-faced object, which has been stitched together in a clever way and then inflated in order for you to essentially imagine, or not just imagine, but play with it as if it were a sphere. And so it begs the question, what can you do if in addition to folding, we also allow you to cut and to stitch? Are there impossibility theorems? Probably not. What are the limits? How can we go with this? I don't know, but that's a good place for me to stop. Thank you very much.
I'd like to open the floor for some questions for Maha.
Yeah.
You mentioned it's impossible to have total disorder, and I was wondering if you were thinking mathematically or physically, or maybe it was a metaphysical remark.
No. There's a whole area of mathematics called Ramsey theory, which comes from combinatorial analysis and number theory, which essentially tells you that it's actually impossible. In fact, there is a very direct consequence of that, which I can tell you offline, which is associated with how many people you need in a room so that at least 3 know each other or 3 don't know each other. And the answer is 6, in fact. So, but that's, yes, so it's not metaphysical at all. There's actually a whole area of mathematics associated with saying that there is, in fact, no such thing as perfect disorder. Because that itself means that there is a pattern. Never mind. Yes?
Anyways, so you mentioned there was a kind of fold where actually put the paper underneath.
That's right.
So it can be seen from neither side.
No, not from neither side. It disappears from the top and it's hidden. And so the other side can be seen from below, but that's about all.
Oh, so it's not a fold where it's basically, you can't see it from either the top or the bottom.
From the top, you can't see the top of some segment, and from the bottom, you can see the bottom of that segment, but that's about it. I'll have to show it to you offline.
What I meant is, it's a specifically, when you fold that paper, there is one side
that can't be viewed, right?
Correct.
Is there a very specific name for that kind of fold?
Maybe, but I just don't know it.
All right, thank you.
Yes?
It seems like I read once that, and I don't think they meant mathematically, but a sheet of paper can be folded a certain number of times. And it didn't matter if it was 10 inches by 10 inches, it could be like
Yeah.
a mile by a mile.
Yeah.
There's only a certain
Yeah.
number of times it
Yeah.
can be folded.
Yeah.
Is that true?
Yes. But there are subtleties to that answer. And the subtlety to the answer is with paper, I can't remember the number. I wouldn't venture a guess. With textiles, with cloth, you can do a few more. What eventually limits you, of course, is that every time you fold, you are basically moving, because it has a finite thickness, you are moving along a curve. And if you're moving along a curve, you end up stretching one part of it. And so eventually it will rip. So that's a physical way of thinking about essentially what limits it. A different way of thinking about it is that as I start making more and more folds, it requires more and more you to do more and more work, and eventually you've got to put it under a 5-ton press or whatever. I don't know.
It didn't seem like a whole lot of folds.
Yeah, it's of the order of 6 or 8. I don't really remember the number. Somebody says 8. Okay, thank you. Thank you, as always. Yes? Paper, 200 BC. The Chinese were folding paper. Yeah, it was rolled out from papyrus and other wood-based materials, which you essentially use lye to break up the fibers and flatten them in water, dry it out, and then in something which is very thin, very easily folds, even if you don't want it to fold. You just dry it, and you don't dry it uniformly, it will start to gently curl. And so that's an immediate invitation to fold. I will let Greg. Yeah.
Last year here there was a talk about Origami and cutting. And the implication seemed to be that it's like a little bit easier. You're less constrained.
Indeed.
So why stick with origami? Like why the constraint of the one sheet? What would you say to this guy on the Origami?
Yeah. Well, so I can also then go all the way and say I just cut up everything into a small number of triangles and glue them in the shape that you want. And that will work too. So again, there is this tension between how much work you want to put in and how much you want to essentially get out. So if I cut up a sheet of cloth or paper or anything into a large number of small fragments, you can certainly do a lot more. There's a lot more work involved. On the other hand, if I start with a sheet of paper, which I only allow you to fold, the constraints are good up to a point. Because you can still do a large number of things, but you can't go all the way. And so the question that you're really raising is, where does the trade-off occur? And the answer to that depends on what kind of tailor are you, or what kind of tailor do you want to be? In other words, how much are you willing to pay a penalty for cutting and stitching versus folding? And that's a very empirical view. That's something that I don't have an answer to. And over time, it's changed. As technologies evolved, we are capable of doing many more complicated things with stitching and with folding. But I don't really have an answer at this point because there is a trade-off, and associated with that, there are costs which have changed over time.
Those models that your students, colleagues built, that you showed us, how many folds typically?
The vase
Yes.
had of the order, so each fold is about 1 centimeter, so that you can essentially get your hands, and it's about 20 centimeters. So of the order of 1,000 or so, maximally. And it was done in pieces and then glued together. If you have smaller fingers and you're an expert, in fact, Levi, over the period that he built these models, he spent about 3 weeks. By the time he had finished, he was able to essentially improve his speed by a factor of almost 3 or 4. So you know where to start. And this raises an even harder question than the simple questions that I told you about, which is how do you try and make sense of the sequential order in which folding should be done in order to get a final shape, and we really don't have a clue. Because the number of states from the flat is very large. But as soon as you go past the flat, then you can make a lot of progress.
Excuse me, how do they start, how do they discover how to start and get going?
You start from the boundaries, and then you move inwards. And there's a class of questions which we've started to address now, which is to essentially switch the problem, and instead of fitting the sheet onto my head or my arm, we just fit it to a strip of my head or my arm and then grow it outwards. And so for the mathematical aficionados, that essentially completely switches the form of the way mathematically you deal with it. So it's like solving a problem for a soap film in one limit versus solving a problem for understanding how waves propagate on a pond. And it's much easier to, in fact, do the second. And that's what we're starting to do. Two more questions over here. Yes. Oh, I was hoping she was going to ask the question.
She whispered.
Okay.
So the origami your students did,
Yeah.
the single sheet ones, you said you couldn't grind them, but wouldn't they all fold flat?
Okay. I told you that there is a constraint associated with the opposite angles being adding up to pi, to 180 degrees. That condition we cannot satisfy. And again, there is a theorem, not due to us, due to a Japanese mathematician, which says that you cannot make a surface which is curved in two directions locally and also have it flat foldable, unless you have an intermediate state between the flat folded state and the fully flat state. And in general, we don't know whether that system exists, that state exists. So that means that you basically cannot flat fold it. If you try to, you may burst a seam. Yeah. There was a question there before.
Just to follow up on that question.
Yeah.
When you had a more simple version, which was just a simple
That's completely flat foldable, and that's it.
that can be.
That indeed can be.
So when you curve it, what thing can you do so that it stays curved?
What do you mean when you curve?
Is there one
No, you give me a.
to keep it, to make it structurally sound, is what I'm saying. To make it really, to stay in that shape, what, is there one thing that you can do?
You have to fix the angle between.
Repeat
Sorry.
the question.
If I understood it, you wanted to ask, can I rigidify it
Yes.
at any state between the flat folded state and the fully flat state? Was that your question?
Yeah.
And the answer is, in order to do that, you have to prescribe creases which are happiest at a particular angle. We assume that the creases are completely free. So that means each facet on either side of the crease can essentially switch without costing any energy at all. But as soon as you put in a finite energy, the system becomes stiff and rigid. I think there was. Okay, yeah?
So coming back to the idea of kirigami.
Yeah.
So kirigami is different from cutting and stitching, right? Kirigami is just selectively removing some.
It depends on your definition. I'm being very
Okay,
liberal.
So suppose
Yeah.
we went to that first
Yeah, yeah.
thing. How does that change the constraints that you have? Does that in fact relax the
Which case? When you're completely cutting and disconnecting, or cutting but keeping everything connected?
Cutting and keeping everything connected, then it's still not stretchable?
Yeah. How does that change? You can do all kinds of crazy things. For example, you can essentially have some part of the material overlap some other part. Okay. If I give you an additional part, another piece of the material, I can stick it in between the parts which have been cut.
So as a mathematician approaching it,
Yeah.
what would change if you were removing some portions of it but leaving the whole thing connected?
So you're changing the topology and you're changing the metric. And so you've got to give me additional conditions on what is happening to the topology and what is happening to the metric. In this case, in the case that I've talked about so far, the metric is essentially frozen. It's the metric of the flat space, in this case Euclidean space. In that case, both conditions are gone. Connectivity, topology is gone, and the metric condition of the metric being the Euclidean metric is also gone. So suddenly the world opens up.
I Googled origami because I was kind of curious to find out some things before you came. And it actually said that it started back in China in 105 AD. Now, obviously, it was passed down from generation. Were they ever able to preserve any of the objects that they made? When were they first discovered? How do we know that that's when it started?
We don't. I don't know the answers to the historical questions about what records have been preserved and what we know. So I just have to leave it at that. I mean, I think I have also read some of these articles that perhaps you looked at, or not the Wikipedia site alone, but also other. I think the actual date varies.
Are there any preserved from thousands of years
I don't know
ago,
the
or
answer.
hundreds?
It's
or-
difficult to imagine.
Especially with paper.
With paper, if it's very dry and if it's not been very heavily treated with acid, it will last. As paper started to become more and more the medium in which people communicated with each other in terms of ideas and money, of course, then the needs went up, and so a large amount of acid was starting to be used in order to essentially first break the wood into cellulose fibrils and then put them back together, and so a consequence of that is yellowing and so on. Of course, now all that is gone. So I'm afraid I don't have a whole lot to add to that.
Can they preserve the works, those objects that you showed us are so magnificent? Will they be able to preserve them?
What we've done is basically spray them with kind of a resin.
Okay, so that's where the
and-
color comes from?
No, the color was just colored paper.
Oh, that's colored.
Yeah.
Maybe one more question, one more.
You speak of energy required to make these folds as such. I wonder if you have a hazard a guess or an estimate of how much energy in joules or ergs it took to make that one of those models your students made.
I mean, it depends on where you want to start counting. You're going to tell me how much he ate, how many hours he spent. So I don't know what the question meant.
No, I
So,
mean the minimum energy required to stretch the fabric at the corners.
oh, it's minuscule.
Ah.
It's very, very small, because even though the amount of stretching is large, it's localized to lines, and so it's nothing, because lines are essentially, they don't occupy any area whatsoever.
Very good. Thank you.
Please join me in